Hello. So today I'm going to share with you of my recent research with my former student Yeo Kwan. And the title is on the F modeling based empirical based estimation of the variances. Okay. So this is a key message. So in this work, we have constructed on capital F modeling based empirical based estimator for the multiple variances simultaneously. And this estimator relies on the estimation of the cumulative distribution function rather than the density function estimation. Okay. So I'm going to explain with more detail what does this mean. Okay. So firstly, let me just briefly introduce the Bayesian empirical based approach. Okay. So we assume that we have the data xi and the parameter we are interested in the theta I. And xi given theta I follows the likelihood, and theta I follows some prior distribution, which is typically unknown. Okay? And then that f of x to be the marginal density function. Okay? So our objective is to estimate the parameter theta I. And in the F-run in 2019, he has classified the empirical based approach as two different categories or two different strategies, which are the F modeling strategy and the G modeling strategy. So in the first one, they are trying to model on the data scale, and second one, they are trying to model on the parameter scale. Okay, and on the example of the F modeling, so this is the Twitty's formula. So basically, assume that the data will follow the exponential distribution family, and the theta I follows some arbitrary prior distribution, G of theta I, and then the posterior mean can be written as the derivative of the logarithm of this function. And this function, you can see that this function only depends on the marginal density. So we know that this posterior mean should depend on the prior, but this depends on prior indirectly. It actually only depends on the marginal density function f of xi. And however, to estimate these parameters, we need to estimate the marginal density function f of xi and its first order derivative. And then this estimation is known to be difficult and challenge, and there are many issues involved in the density estimation. Okay. So now we want to try to study the estimation of the scale parameter or the estimation of the variances by assuming that the existing the data which is the sample variance SI squared. So SI squared given sigma I squared follows the scaled chi-square distribution, and sigma I squared follows some prior distribution. So in the existing literature, there are many attempts by assuming that this prior will follows a parametric assumption like inverse gamma or log normal, a mixture of inverse gamma distributions. Okay. So in this work, actually, we assume that this prior will follow any arbitrary prior distribution, G of sigma I squared. And then we let f of s squared to be the marginal density function of the sample variances. So to derive the base estimator, we consider a few different choices of the loss functions. Okay. And the first one actually is the squared error loss, which is not very widely used. For the other three, they're all scale, they're all unit free, unit invariant. And L1, L1, and L1 prime, we just swap the position of sigma I squared and sigma I hat squared. And L2 is also known as the standard loss function. Okay. So based on the three different loss functions, we can derive this estimator. For instance, for assuming L1 prime, then we have the Bayes estimator, which depend on the marginal density FSI squared and its first and second order derivative. But we know that estimation of Fs squared is already changed, not even to mention about first and second order derivative. And the second one, by assuming standard loss function, this expression is much simpler, but it still relies on the marginal density and its first order derivative. So very interestingly, if we assume the loss function L1 and then the resultant Bayes estimator actually depend on the data through its marginal cumulative distribution function. Okay. So because for the third one, it depends on the cumulative distribution function, and the cumulative distribution function can be easily estimated by using the empirical distribution function, and therefore by replace this Fs squared by the empirical distribution function, we have the empirical based version. Okay. And we call this as capital F modeling based empirical based estimator, because this estimator depends on the data through the capital F through the cumulative distribution function, not the density function. Okay. But the cumulative distribution function has many advantages. For instance, estimation becomes instantaneously, and secondly, the empirical distribution function will converge to the true function uniformly. And because of this, actually, we are able to extend this estimator easily to the two different problems. One is known as the post-selection inference. So in this case, actually, we are not interested in all the parameters. We might be interested into the variances corresponding to the data with smallest sample variance, for instance. Okay. And when we focus on this parameter post-selection, then how to estimate the corresponding variance, and this F-EBV can be easily extended into this situation. Okay. And another situation is called the finite base problem proposed by the Efron in 2019. So this is that in addition to the data that we can construct our estimator, assume that we have a newly arrived data S0 squared. And then we are interested in the estimation of the corresponding variance sigma 0 squared. And then capital F-EBV can be easily extended to this problem. Okay, so in this case, we introduce a capital F modeling-based empirical-based estimation for the variances. Okay, so next we can study some analytic properties. So, and especially we want to know what is the difference between the empirical-based version and the true base version. Okay, and because in this case, actually, we just replace the capital F S squared by the empirical distribution function. The empirical distribution function is known to converge to the true distribution function uniformly. And therefore, we can show that both numerator and denominator of the empirical base version will converge to the corresponding terms in the base version uniformly. Okay? But when we consider ratio, unfortunately, the denominator will converge to 0. And then we have to exclude that from this analysis. Okay, and therefore we consider D of data a set. And this set actually goes from 0 to a very large number. So it's a very large set. So as long as this SI square falls into this set, then we have this uniform convergence. Okay, so this guarantees that this approach will work very well, even for the selected case. Okay. And the next one actually will go through very quickly about the numeric studies. So in numeric study, we consider the estimation of the sigma squared for the post-selection. We also consider finite base inference. Okay? And then all this result, we have considered many different settings. And then we can imagine that the capital F-EBV had the best performance. Okay? For instance, the base risk is the risk is smallest among all the existing methods that we have considered. Okay? And then actually, so because of the time limit, I'm going to another interesting thing called for the real data analysis. Okay. So in the real data analysis, actually consider two microarray data sets, leukemia data and colon cancer data. Okay. So in this study, actually, what we want to study is something called a discordance. So here's what we have considered. For any given data, we randomly split the data as group A and group B, okay, and each one has approximately the same number of subjects. Okay. And then we construct intervals for all the parameters in both group A and B. And then we claim a gene to be significant if the corresponding interval doesn't include 0. And then we call gene to be discordant if it is declared to be significant for one group, but not for the others. Okay. And then we report the percentage of the discordant genes. Okay. And then based on the different estimation of the variances, and then this is the plot. So the last one is the proposed method, capital F-EBV. It is shown that this one will lead to the smallest number of the rate of the discordance. This is for the colon cancer. And for the other one, for the leukemia, we have the same conclusion. Okay. So this capital F-EBV will give us a decision. We have the smallest number of the discordant decisions. Okay. And therefore, this method is definitely preferred to use in the applications. Okay. So last one, I just want to give to a quick conclusion. So we propose capital F-EBV. This is a new method, assume the arbitrary prior distribution. And this method relies on the data through the marginal distribution function only, avoiding the difficulty of estimating density functions. So number 3, this estimator can be calculated instantaneously, and it's shown that this will perform much better than all the competitors. Okay. And here's a list of all the references. So that's all for my talk, and thank you very much.